there's one riddle I want to offer you, and if all goes well, you're able to better reason about this example, or this riddle, if you will, once the lecture is done. So perhaps this is a situation that looks familiar to you, but perhaps it isn't. Then just know that some people have encountered this situation in which they thought in their dating life that it's important to them that the people they choose for a date are attractive or nice. Of the people that person selects from Tinder for a date, they have the impression that they seem to get more annoying the more attractive they are. So there seems to be a negative correlation between how annoying a person is and how attractive that person turns out to be. And the nice persons often are a bit ugly. So basically, so what the person is noticing in their dating life is that sure, there are attractive people to date, but the probability once a person gets more attractive that the person turns out to be less nice or more annoying it increases as well. So those two concepts are correlated, if you will. So I don't know whether you recognize this from your dating life, right? Basically, all the attractive people you date turn out to be assholes, and all the people with let's say the personality you're seeking for are perhaps less attractive. I don't know. It might sound like familiar. It might not sound familiar. But there's a reason for this. And there's a proper way of understanding this problem related to the concept of causality we're going to talk about. All right. We'll get back to this after the following. So we're going to talk about correlation does not imply causation. So basically, we're going to reiterate a lot of the stuff you already know, right? So you know, correlation doesn't necessarily mean that there is a causal relationship. You talked about this at length in the first block, and perhaps in the school you did before that as well. But we're also going to move beyond just saying correlation does not imply causation, because perhaps that's not a real satisfying way of thinking about it. Because if it doesn't imply causation, what does it imply? And what can we say on the basis of correlational technique? Because in a lot of cases, that's what we're stuck with, right? We can't do that experimental control in a lot of research type situations. So does it basically mean that we can only talk about correlation? And is that interesting in any way? And what can we specify about our research results if we're stuck with correlations? So we're going to basically refresh your memory on the difference between correlation and causation and what a causal relationship actually is. And we're going to move beyond that in talking about different ways of specifying your assumptions and then testing your theories using correlational data sets. You know, of course, that correlation doesn't imply causation, and that's something that's one of your first instinct as a critical thinker, right? After the first year. So if you noticed stuff like this on the internet, some journalist concludes that if you like curly flyers on Facebook, that means you're clever, right? That doesn't necessarily mean that eating curly fries makes you smarter, right? So if there is a correlation, a predictive relationship between eating curly fries or liking curly fries and being clever, that doesn't necessarily mean that the one causes the other. It's difficult to come up with a different explanation, by the way. So this also shows you that if you have a very large set of data, some stuff will be predictive of other stuff in the data set, even though we're unable to explain why, right? So why would it mean that people who like curly fries on Facebook have a higher probability of being clever or higher IQ score than others? I don't know. But you should at least recognize that the fact that we have that correlation or that predictive relationship doesn't necessarily mean that we have a causal relationship as well. Perhaps you remember this because we also covered this in the first block when talking about the causal fallacies. The reason why we can't just conclude on the basis of a correlation that there is a causal relationship, we can use the classical definition of causality from John Stuart Mill to better understand this. So we talked about when is something a causal relationship. So when can we actually say that X causes Y? Well, only if and only if there's a case of priority. So X precedes Y. So first X happens and then Y happens. There's a case of consistency. So changes in the occurrence of x occurs or not, and then y occurs or not, they vary systematically with each other, which is another way of saying there's a correlation between x and y, right? So the likelihood of x occurring affects the likelihood of y occurring. And exclusivity. So there's no alternative explanation for the relationship that we've observed between x and y, or that correlation that we've observed between x and y. So that helps you, right, in reasoning about why can't we say on the basis of that correlation or predictive relationship between curly fries and intelligence that there's a causal connection? Well, because we only know that there's a correlation, and then we don't know what occurred prior to what, so what the priority, if there's a case of priority, and we don't know whether there is an exclusive relationship between the two, or whether there are alternative variables that play a role as well in explaining a causal effect. By the way, these three criteria, it's not just that some philosopher is saying, well, you should just use those criteria and okay, I'll accept it and check those three criteria. No, it's basically what we use when learning about the world as well. So if you manipulate in an experiment, for example, information that you get related to these three factors, so first the one occurred and then the other, and there's potentially an alternative explanation or there isn't, right? So if you vary those in an experiment, you see that people are more likely to conclude that there's a causal relationship if these three factors are present, and they're less likely to conclude that there's a causal relationship if one of those factors is absent or if all of them are absent. So basically it's how we observe the world and how we come to conclusions about causality in general. That doesn't mean that we're always right. Of course, we look for information related to those three criteria, but it's often difficult to properly get, well, good data on all three. Particularly, it's difficult to properly specify what the third criterion means, as we're going to see soon. But let's just try out those three criteria. So if I were to tell you that problematic academic achievements, drug abuse, pregnancy at a very young age are related to low self-esteem, can we then conclude that if we create a stronger positive sense of self-esteem, those other problems will disappear by themselves? What do you think? Basically, given these observations, can we conclude that there's a causal connection? And what criteria are met or aren't met in this case?
No, because the priority isn't given.
Right.
Like, it isn't said that what was it? Yeah, that one is before the other or occurs before the other, so we can't know which is causing what. Right.
So we don't have any specific information about priority. So what occurred prior to something else? So it's difficult to say. And even though the conclusion I asked, does it follow from the information given here, does assume a specific temporal relationship between one and the other, right? So changing positive self-esteem will cause the other things to disappear. So there's an assumption of priority of self-esteem over the other problems, even though that's not reflected in the data. And there's, of course, there could be potential third variables that would explain this relationship as well. So there's no case of exclusivity as well. All right. Another example, people with poor reading skills make more erroneous eye movements, go back to the beginning of the sentence more often, which is called regression, and have more fixations per line of text. Does that mean that abnormalities in eye movements, or in your oculomotor skills, cause poorer reading skills? So again, I'm asking you, can you draw a causal conclusion between one thing and the other, abnormalities in how you use your eyes basically when reading, and your reading performance on the basis of the stuff described at the top?
There's no exclusivity.
Sorry, there's no?
Exclusivity.
All right. What could be an alternative explanation here?
Poor concentration.
Yeah, poor concentration. So something else, some cognitive skill or occurrence in that case, that would have an effect on both in this case, both the abnormalities in the eye movements and the poor reading skills. And of course, priority isn't exactly clear as well in this case. All right, so let's move to the final example, which is a bit nasty, but which will make for sure that, these three criteria stick around in your head after the lecture. So again, I think it was in the 1800s somewhere. I think Goldberger was doing research on a disease called pellagra. And pellagra makes your skin look very scaly, and well, it's a bad disease to have. And on the basis of the data he had and the spread of cases over the areas in London, again, I guess he did the research. He reasoned that, well, it correlates, or the disease is probably related to bad sanitary, how do you call it? Circumstances, right? So no flowing water or no clean place to wash your plate, for example, or bad dietary situation. So it's a lack of a proper diet or lack of hygiene that would cause this disease. Both would would be a good explanation for the fact that the disease occurred more often in areas where people were very poor, because they both didn't have good food to eat, and they didn't have a good sanitary, no flowing water, etc. So what he did to test his hypotheses, so what he wanted to test, he wanted to falsify basically one of those two assumptions, and he did that by doing the following. So what he did was, we're just going to present you with the description of the actual research. So he selected two patients that had that pellagra, that scaly disease. One with scaling sores and the other with diarrhea. He scraped the scales from the sores, mixed the scales with 4 cubic centimeters of urine from the same patients, added an equal amount of liquid feces, and rolled the mixture into little dough balls by the addition of 4 pinches of flour. The pills were taken voluntarily by him, his assistants, and by his wife. So there you go. He's taken the excrement of people that actually suffered a disease, baked it into little brown balls, and fed it to himself, his research assistants, and his wife. Just to show you what distance you can go as a researcher, right? What happened was that no one who were fed those feces ball got actually ill. So that showed him some information related to consistency for the sanitary conditions explanation, right? So if indeed bad sanitary conditions were the cause of the spread of pellagra in those poorer regions of London, then you would expect that the most extreme thinkable version of that causal explanation, actually eating the excrement of other patients suffering the disease, would make for sure cause the disease in you as well. That didn't happen, so that showed that lack of consistency in that final example. All right, so I hope that sticks around. The reason why I'm talking about these different examples is just to try out those 3 criteria, right? So the priority, consistency, and exclusivity criteria apply to different examples. Just to show you that what we mean when we talk about a causal relationship is something in which those 3 assumptions hold. People struggle with this, right? It's difficult to properly reason about causality, which you can see in different thinking errors related to causality. So, for example, I'm going to give you 2 different tasks. I'm sorry for that. The first one, perhaps you know this already. Don't give it away for the other people. So basically, you're a mechanic working on planes, and there's war going on, and your task is to fortify the planes that return from battle with thicker armor on the places where it turns out to be needed. So being a good statistician, being a good researcher, you make a graph of the most likely places where, well, all the different places where bullet holes occurred on the planes that returned from battle, which are depicted with the red dots on the plane. The question to you then is, where should you decide to apply the thicker armor on the plane, given the different bullet holes that you found?
In the places where there are the most bullet holes?
Right. Why the places where there are the most bullet holes?
Because that's where there would be the most likely chance that a bullet would hit again. So that will need the most protection.
Okay. Thanks. Yeah, that's a good intuition, right? I think most people were thinking, yeah, I'm graphing these bullet holes, so it makes sense that I'm putting up the plates on the places where the planes that returned from the war were shot the most. That's where they needed fortification.
It's the places where they're not bullet holes, because those are the places where if the planes got hit, they didn't return.
Exactly. Very good. Thanks for that addition, because what we tend to neglect here is the fact that not all planes will probably return from battle in the war, right? And the planes that did return had bullet holes apparently in places that were not fatal to the flying ability of the plane. The planes that did got shot down, they didn't return for your assessment, so they aren't included in this graph, and that's something we need to bear in mind. This is one of those, well, causality-related thinking errors. This is one of the threats to causal inference mentioned in the chapter by Stanovic for today, which is called attrition, right? So some of the participants in your research might drop out, for example, in a similar way that some of the planes in your sample have dropped out as well. And the people that dropped out of your research, or the plane that dropped out of the war in this case, might point your conclusion in a different direction if they were still included in the sample, which is an example of attrition, which is something that throws us up when reasoning about causality. Let's talk about another intuitive example related to those threats to causal inference, which is the Sports Illustrated jinx. And the cover here asks whether the jinx is for real, and the jinx is that the idea is that you get to be on the cover of Sports Illustrated if you did really well in your field in a given year. So you're very good in baseball, and then you would land up on the cover of Sports Illustrated. And the jinx would be that if you have been on the cover of Sports Illustrated, the likelihood is that you perform much worse in the years beyond that, right? So in the years after you've been on the cover, your performance basically suffers. And people think that's the jinx, right? So you were on the cover, and that impacted your performance in a bad way somehow. Or is it something else going on here, right? What would explain this occurrence? What would explain this data without saying there's a jinx to being on the cover? Yes, regression to the mean. Could somebody explain why this would be an example of regression to the mean? No?
Someone might perform really well for how he normally performs, and then gets to the cover illustration.
Right.
And after that, he will perform how he would normally perform, and like his whole streak, so to say, in sport terms, will be over. He will perform worse than before the illustration.
Right. Indeed. So a factor in performance in sport, not the complete explanation, but a factor is, well, some random stuff happening, right? The right conditions, the right opponents, the right year in your development, etc., etc., etc. And sometimes all those add up to a great performance, an exceptional performance. But it's unlikely that all those factors will line up in a similar way again and again and again, year in, year out. So if you've noted an exceptional performance, it's more likely that the performance will be worse in the years after, because their performance will regress towards the mean. So this is another threat to causal inference, right? So regression towards the mean is one of the reasons why you might notice a pattern in the data, even though we're not dealing with a causal relationship, which is mentioned again in the Stanovic article for today. We're talking about ways in which the data can throw us off, can lure us into thinking that there is a causal relationship even if there isn't. And we've talked about two examples, two threats to causal inference, regression towards the mean and attrition. And we can also think back to the different causal fallacies that we talked about in the first block. I'm going to briefly mention them here because they're all three related to those three criteria we talked about, to priority, consistency, and exclusivity. So if someone were to argue just on the basis, only on the basis of information relating to priority, that there is a causal connection, whilst ignoring the other two criteria, we're dealing with the post hoc ergo propter hoc fallacy, right? After this, therefore, because of this, which is literally one of the fallacies in reasoning about causality. Taking one specific item of information, in this case related to priority, ignoring the rest and concluding that there's a causal connection is one of the reasoning errors about causality on the basis of, just part of the information that you need to be able to draw conclusions about causality. The other one, of course, we covered already, just on the basis of that consistency relationship or correlational data, claiming that there is a causal effect without looking at exclusivity or without looking at priority, mistaking correlation for cause. And the final one we also covered in the first block is the inversion of cause and effect. Even though there is priority and there is correlation, that doesn't necessarily mean that the cause we're looking at is the only potential cause of, only possible cause of the effect we're seeing. So taking away that factor, that potential cause, that specific cause, doesn't necessarily mean that the effect will no longer occur, because it might not be the only cause of the effect. So basically, three thinking errors: post hoc, ergo propter hoc, after this, because of this. So confusing information related to only priority for being able to draw a full conclusion about causality. Mistaking correlation for cause, just on the basis of correlational data, claiming that there's a causal effect. And inversion of cause and effect, just on the basis of information of the first two, drawing the conclusion that this is the only possible cause, which is where we run into some problems, because it's difficult to specify what we mean by that exclusivity, right? We can't necessarily say that all the stuff we call causes in psychology or in other fields are only exclusive causes, right? So if we talk about smoking causes lung cancer, we don't mean that smoking is the only way in which you can get lung cancer, right? So we run into a bit of problem using this classical definition of causality. We particularly in applying the exclusivity part of that. So we need to be more explicit about what we mean by the final criterion, and exclusivity might not be the best way to put that.